and that guitar string is oscillating at 440 hertz. And then that wave goes from being on a string, a metal string, into the air, which is a completely different thing, a different material. And yet, you can still hear it as 440 hertz. So the thing that is the same when a wave changes medium, the thing that's preserved is the frequency. The speed of the wave may change, the wavelength may change, but the frequency is the thing that you can count on. As that wave travels through all sorts of different materials, that's the thing that stays the same. Okay? So, this brings up an interesting point about visible light that I just mentioned. I wish I had saved it on the board. We said that the Roy G. Biv, the frequency we said was 430 terahertz to 750 terahertz. And that frequency you can count on, that frequency range, no matter what, is visible light. Red is always 430 terahertz. Violet is always 750. But I then also proceeded to say that the wavelength range was from 700 nanometers to 400 nanometers. Well, there, I have to tell you now, that's just vacuum wavelengths. Those are computed with the speed of light in a vacuum. What about if I went into a material where n equals 2? Well, red light will now be 700 over 2, so that's 350. And violet will now be 400 over 2, that's 200. So this is a point that is rarely made when people are talking about the visible light. You might get the habit of people saying, oh, you can't see 200 nanometers. Well, that's true if it's in a vacuum, but 200 nanometers is violet if someone's sending you that wave in a material. Okay? So there is no single range of visible wavelengths. When people say that there is a range of visible wavelengths, they really mean vacuum wavelengths. The wavelength is totally negotiable based on what material that wave is traveling through. The thing that is constant, that cannot be changed, is this. So in a certain sense, that is the better way to refer to colors. Because the frequency of red is the frequency in any type of material. You can count on red being red, being red, being red. Frequency, frequency, frequency is preserved, even though the wavelength of that same wave might be all different things as it travels through different materials. Okay? Are there any questions on that? Okay, so that's a little bit about what happens when a wave enters a material. And at this point, I think we are ready to start with the major study, topic of area. Anyway, homework 8 and homework 9 is going to be based on the following, something called geometrical optics. So geometrical optics, as the name implies, has something to do with geometry. Namely, our primary interest in this is going to be the path of travel of the light. And as we are analyzing that path of travel, we will basically have to analyze the geometry of how it bends and it moves around. And in order to do this, all we need is a light ray. Yes, the light is, of course, waving. It has waviness, but the only thing that we are really interested in this topic is how that direction of that ray will change. We'll do several topics on this, and then we will move to the next class of optics called physical optics. And physical optics is where we remember again that light isn't just an arrow, it is a wave, and there is a waving to electromagnetic variation. And so therefore, we can look at interference phenomenon like we did at the end of Physics 1. Okay? So that's basically the course. Geometrical optics is homeworks 8 through 9. And then physical optics, which is when we remember that light is actually a wave too, that will be homework number 10. And homework 10 will also have a smidgen of modern physics or quantum physics, depending on how much we get a chance to get to. Okay, so that's kind of where we're going to close out the class. So, our first topic in geometrical optics, let's revisit that thing we were just talking about. I'm going to orient it vertically now, because no good reason. I have a vacuum. I have a material. And I'm going to once again send a light beam from the vacuum, and now I'm going to do it at an angle. So remember that when we describe the light in terms of how it comes in, we describe it in terms of the angle the light beam makes to the normal line. Okay? So we've already established that there is a reflected beam. So this is the incident. This is the reflected beam. And we've established that there is the reflected angle is just the same as the incident. But I have to tell you that, as you are probably aware, that there is also a part of the light that can go into the material. I just talked about light passing into material. Perfect example would be a piece of glass, right? You send light toward a piece of glass, well, some light will bounce off, right? You can use a piece of glass as a mirror at night, right? When there isn't too much light flooding from the outside. But part of the light obviously passes through because someone outside can see you, you're in here, right? So, generally speaking, when light comes in and interacts with the surface, some of it will bounce off and some of it will go through. So we call this the refracted beam. And the angle here, which we again measure from the normal line, we can't use, unfortunately, reflected and refracted both start with R. So I'm going to call it theta sub t. T is for transmitted, right? So it's the part that is transmitted into the material rather than bouncing off, okay? So one of the things that you can say, of course, is that the energy has to all be there. And so you can say that the intensity in the reflected beam and in the transmitted beam has to, of course, come from the incident beam. This kind of looks like your junction rule, although, of course, this is not current, right? This is intensity. This is just a statement of energy conservation. Now, here's where I tell you something we can't do. While you should understand conceptually that this energy in the two outgoing beams is all coming from the incoming beam, I can never ask you what percentage goes into either one. Okay? I can't ask you, is it 25%, 75%, 50%, 50%? I can't ask you that. It's beyond the scope of the class. Okay? The only thing that you know is it has to all be there, but it turns out that how much goes into one beam versus the other is a more complicated calculation that depends actually on what the material is and what the incoming angle is. So it's not, of course, you can compute it. There are equations to do it, but they're beyond the scope of this class. There's only one exception. So the one exception for doing this quantitatively is there is a case that we'll do a little bit later where 100% of the light is reflected and none is refracted. This is a phenomenon called total internal reflection, or TIR for short. Now, as far as what is the internal part, we'll get to that, but I do want to point out, otherwise it's pretty much in the name, total reflection, right? 100% of the light is reflected. I cannot ask you in any other cases. So no other cases I can ask you for quantitatively. You are not, it's beyond the scope of the class for you to be able to calculate what is the split of energy in the two outgoing beams compared to the incoming, although of course you should understand all the energy should be accounted for on a conceptual level, okay? So, before we get to total internal reflection, we have to establish some basics about this refracted beam. Now, we just talked about that the light slows down, and if we were going to remember that the wave is wavy, we know that the frequency is unchanged while the wavelength is reduced. But the next order of business is, what about the direction of travel? It turns out that the direction of travel can change. Okay? So let's talk about refraction a little bit more. And what I aim to do is, on a conceptual level, try to explain to you how the light bends its path of travel potentially. And the only thing you need to know is that there's a principle called Fermat's principle of least time that light operates with. It turns out that, in fact, many different phenomena in the natural world go by something like this, principle of least time. What does that mean? Is that if there is a path between 2 points that light can travel in the least time possible, that is the path it will take. Light will travel from point A to point B in whatever path takes the least possible time. Now, least possible time does not necessarily mean the shortest distance. I'm going to show you that those two things do not always apply to each other. This applies for human beings as well. You probably know, if you spend enough time in traffic in the Bay Area, that the getting from point A to point B in the fastest time is not necessarily taking the most direct route, right? So let's take a look at a more simplified system. I'm going to have a beach. Okay, so here's the beach, and here's the water on this side. I'll have a drowning swimmer. And I'm going to have a lifeguard over here that's going to have to make some quick decisions about how best to save the life of this drowning swimmer. And of course, the same deal is, it's imperative that you get there in the least possible amount of time, right? So let's take a look at possible strategies for doing this. Well, of course, you might say, why don't we just take the shortest distance? That is not going to be the most effective solution, because, as you probably know, most people can run much faster on the beach than they can swim once they get in the water, right? So the problem with this is, while it is the shortest distance, it'll put you in the water for too long. So then you might say, well, isn't the best solution then to just run on the beach as long as you can and then swim the least amount? But the problem with that is that you go too far out of your way. Yes, you'll run further on the beach and swim as little as possible, but it is too far out of your way. It turns out that the very fastest approach is to do a middle ground between these two. So do something like this. That's the best of both worlds. It doesn't have you go too far out of your way, but it also does leverage the fact that you can run faster on the beach than you can swim in the water. Notice that you've extended your beach travel a little bit, and you've shortened your water travel a little bit. That is the optimum method. That is the least time. Okay? So what would be the corresponding situation in a material? So the corresponding situation would be this. If you are in a smaller N material, I'll call that N incident. Maybe it's not a vacuum, but it's an N material where I'm coming from. And then I go into a higher N. So I'm going from a material with a lower N to a higher N. Now let me remind you what N is, right? N is the divider here. So what that means is that you're going faster over here, and you're going slower over here, right? Now you have to divide by a larger N, so your speed will be less. That is the exact equivalent of the scenario I just drew, right? You can run faster on the beach, swim slower in the water. You go faster in this material, slower in this material. So light will bend. It will bend exactly how I drew it, like this. So light will bend toward the normal. Another way to think of it is that if the n value increases, then the theta decreases. Since I'm going into a higher end material, I'm going to have to bend toward the normal, so my theta t will be smaller than my theta I. Okay, so that's the first case. Now let me present the next case. Let's say instead of, we still have the drowning swimmer, but let's say that this lifeguard has gone off duty, and we have a new lifeguard, and this is going to be a rescue SEAL. I don't know how to draw a seal, so if you can do a better job, go ahead and do that. Now a seal, of course, has exactly the opposite problem. A seal, it looks pretty good in the water. We can zoom around the water, but they flop along really slow on the beach, right? So their strengths are your weaknesses and vice versa. The path is now going to look something like this. That's the optimum path. So they should spend longer in the water and less time on the beach if they're going to overall minimize their total time to rescue. Shouldn't go too far out of your way. Shouldn't try to take a straight line. Try to strike a balance between them. Okay? So, if we draw a picture of that over here, the equivalent would be being in a higher end material going into a lower end material. So here, if you're in a higher end, you're traveling slower. And then over here, if your n gets smaller, you're traveling faster. So if I draw this path, here, you'll bend away from the normal. If n gets smaller, theta gets bigger. Oh, and I should draw the light arrow that's going from here to here. So hopefully I've convinced you that flowing from the principle of least time, light should bend like this. Bends toward the normal when you go into a higher end, it bends away from the normal when you go into a smaller end. These things are really nuts and bolts basics. These should become second nature, knowing when light bends toward versus away from the normal. So, what can we do with this? I guess quantitatively, well, let's do the qualitative first. I will say that the amount that n changes by will affect the amount of the bending. And hopefully you see how that follows, right? If your n changes very little, then your bend is very little. If there is a stark difference in the n values, indicating a huge difference in the speeds that you can travel, then your path becomes more bendy itself. Right? So if you have a big n changes lead to big bends. Okay? So a big n, I guess I'll call it big delta n, leads to a big delta theta. You will see the most extreme bending when the n value suddenly has a huge step. Now, of course, which way it changes affects whether it bends toward or away from the normal. So if you're going into a much larger n, your bend to the normal will be huge. If you're going into a much smaller n value, your bend away from the normal will be huge. Or if it helps, think of it the other way, right? If the n change is basically tiny, you'll have a tiny bend. And in the limit that the n value doesn't change at all, then you won't bend at all. There's no reason to bend anymore, right? So if you have an n value and you have another n value that's the same, why would you bend at all? Then quickest way from point A to point B is just a straight line. So if that, by the way, there's an interesting conceptual question that's going to come up on your homework 8. It's 0 points, so I don't feel like I'm giving anything away, but it is you put a glass eyedropper into the right solution and you can't see it anymore. So that's going to require you to think about how is it that you see transparent objects in the first place? What allows you to see a piece of glass even though it isn't dirty, right? How do you see something? Well, it's because it bends the light from the air going through it. So what you're really doing when you see a transparent object is you're looking at something behind it and you see that the light from something behind it gets warped. But if you then put a glass dropper in with an n value that is the same value, you're going to not see that bending anymore. You can make things totally disappear. If you've ever done dishes in the sink, right, and tried to find the glass underwater, it's much more difficult. It's harder to see glass underwater. And that's because the light does not bend as much going from water to glass as it does from air to glass. Now, finally, to make this all quantitative, I will point out that these two seem to have an inverse relationship. When one increases, the other decreases, and vice versa. So you might actually wonder, is the law of this? It's not quite. So I put a squiggle in between. Squiggle is the technical symbol for sort of-ish goes like. Okay? So it's basically kind of meant to show you that the two have an inverse relationship. If you increase this, you'll decrease this, or vice versa. To make it an actual equation, it's got a sign function in it. So the actual equation looks like this. I don't think it's worth deriving why there's a sign in there. This is the law of refraction, also known as Snell's law. Law of refraction, more commonly known as Snell's law. Now you might see the sign in there and think that's going to muck things up, but in fact it doesn't really. It's just a minor modification. Here's why. These angles have a maximum range of 0 to 90, and that's all they can be, right? And so if you look at the sine function between 0 and 90, it's pretty boring. It just grows. It doesn't grow like a straight line, but as theta increases, sine of theta increases. So when we're just looking at proportionalities, we can basically all but ignore the sign. The sign will change the slight number detail, but it will not change the basics of when n goes up, theta goes down, and vice versa. Okay, let's call it a day there, and we'll pick up some more stuff on this on Tuesday.